We're in chapter 14, and we're starting with section 14.4, which is RLC circuit. So that would be I could have a resistor, an inductor, and a capacitor in series, or I could have a resistor, inductor, and a capacitor in parallel. Those are my two choices. Clearly there's a third choice, but I don't think we do it in chapter 14, and that is we could put a resistor there, an inductor there, or we could put a inductor here and the resistor there, or we could put the capacitor there, and we could do something like that. So there's other ways that we could make those circuits, but we're just going to be talking about things that are in series or things that are in parallel. If I have something that's in series and I look at for the impedance, this is going to have some value x of c, some reactive value x of L, some reactive value R, and my impedance is going to be the quantity of the R guy squared, and then the x of L is going to, and x of c are going to subtract from each other, and I'm going to square it. As you recall, the x of c is in the positive imaginary I direction, the x of L is in the negative imaginary direction, and the resistance is always on the positive, is always on the real axes when you're looking at a graph of those guys. So I have to subtract the x of c from the x of L to find out who's winning, and then I can find out what the impedance is. If I want the angle, I'm going to have to do the same thing. I'll take the arctangent, and I'm going to have the real guy on the bottom, and then I'm going to have this XL minus XC on top. And if that happens to be a negative number, if the XC guy wins, then this is a negative angle that I come up with. And if the X of L guy wins, and then this will be a positive angle that I come up with. So that's the math of the situation. The author shows it slightly different than that, but those are the calculations you're going to have to run. On page 441, we see that we have some frequency response of these guys. And when you do your lab work, you're probably going to see about the same thing. So there's going to be some frequency that's whatever it is frequency. And as I pan, my phase shift is going to shift from a positive 90 to a negative 90 degrees as I go through that resonance frequency. And the resonance frequency is 1 over 2 pi square root of LC. I hope. And that pretty much covers that. Now, if I'm in parallel, things are going to act a little different. So if I'm parallel with my resistor, my capacitor, and my inductor, that doesn't look much like an inductor, does it? Now, back to the important issue. I never performed that song in any musical. I was the spotlight operator. So for an entire summer, every Friday and Saturday night, 10 weeks, maybe 20 performances plus rehearsals, I got to man the spotlight. So that's how I learned that particular song. All right, so now it's not an issue of what the voltage is, because the voltage is constant. It's a parallel circuit, right? Now it's a matter of what is the total current. So the total current is going to be the current through the resistor squared, plus, I'm going to take the current through the inductor minus the current through the capacitor, and I'm going to square it. So the same thing is happening in this circuit. I've got current through the inductor, I have current through the capacitor, and I have some real component. The two imaginary components are going to cancel each other out to whatever extent they do, and then the total current is going to be that formula. And the same thing is true if I'm taking the angle. I'm going to take the arctangent, and I'm going to have the current on the bottom, and I'm going to have this IL minus IC on the top. And I'm going to have IC minus IL for current. IC minus IL. In that case, it doesn't matter because I'm squaring. It doesn't matter, but in this case, it does. And the current is going to be negative when I'm inductive and positive when I'm the other way. Because V is equal to IR, is it not? V is equal to IR. So current is going to be voltage divided by X sub whatever it is. So when it's X sub L, then this is going to be a positive 90 on the bottom. It's going to be a negative 90 on the top. So this is going to be magnitude angle minus 90. So the X of L guy becomes the negative way of going places. Okay, I think that covers just about everything. We still have power considerations. I guess we better talk about that. 14.4.9. So we have power that's apparent. We have power that's reactive. We have power that's real. Okay, so my real power is going to be on the x-axis. That doesn't look like a P though, does it? And then we're going to have power that's reactive, and that's going to be the power caused by the capacitor minus inductor minus the power caused by the capacitor. It's going to be either in the positive or negative direction. And then we're going to have apparent power, and the apparent power is what I am paying the power company for. So my power apparent square root of the real power squared plus power of the inductor minus power of the capacitor squared, however that works out. And my power factor, capital PF, I could spell capital PF, power factor is going to be that real component divided by the apparent component, which is also the cosine of the angle, that angle there. So the definition of the cosine of the angle, which is my power factor, is the real component divided by the apparent component. So that would be the cosine stuff. Okay, well that's probably good enough. Let's see if we can solve some problems. You say I have to start on 14? 19? Now I have to do this without a calculator, so that will be a slight bother. But I do have a handy dandy scientific one sitting here. So I'm going to calculate the values for the circuit A. I don't know, 457. Okay, so I got 12 volts, 18 ohms, 180 ohms, angle 90, and I've got 180 ohms, angle minus 90. Well, that makes the problem easy, doesn't it? All right, so we want voltage L, and we want voltage C, and we want voltage LC. All right. So those are the things we want. So we'll ask ourselves, what is the impedance? The impedance will be the square root of 18 squared plus 180 minus 180 squared, also known as 18. The current total is going to be the voltage, 12 volts divided by 18 ohms. What is that? 2/3? 2/3 of an amp. So the voltage across the inductor is going to be 180 times 2/3. 120 volts. And the voltage across the capacitor is going to be 180 times 2/3. 120 volts.
Is that 180 or 18 ohms?
180. Yeah, 180 ohms for X sub C. Yeah. The voltage inductor to capacitor is going to be 0. It didn't ask us, but the voltage across the resistor is going to be 12 ohms, 12 volts. Didn't ask us that one. Okay. How many believe that? Anybody believe that? Got to be pretty hokey, right? That's pretty silly. I got 12 volts on my source, and I've got 120 volts across two different things with a 12-volt source. Somebody must have gone and had their head examined someplace. Maybe we should get what's his name in here to teach the class for us, you know. Paul, yeah, that's what we need. Now.
That's a good joke, thank you.
You like that one? Yeah. Maybe we should. That'd help me out. I could then be in my office uploading videos. Wouldn't that be good? Huh? Am I recording this one? I think so. That's what these green things are flashing for. Oh, I hope I put the volume on. Now, what's the problem with doing this in multisim? Anybody know what the problem is? You don't know. Is that what you're trying to tell me? You don't have a clue? Where am I going to get a inductor that's 180 ohms? Huh? Alright, so there's an inductor. Where is the 180 ohm one? It doesn't exist, right? There is no such thing as a 180 ohm one. How about a capacitor? Can I find a capacitor that's 180 ohms?
Probably not. No. I go with no.
No, I can't. All right, so but then why am I doing the circuit for? if I can't draw it. You know?
You imitating proof? I know.
You know, maybe this will just be a test question. We'll just have somebody do it for us on the test, and then I won't have to worry about it. All right, so I got that. All right, so now I'm going to instrument it. What is this guy doing in the way anyway? Anybody know? Voltmeter. So we want one here, one there, one out here, and we'll throw one over here for good measure. Any of these things work? No, they're all DC stuff. So I have to change them all. I'm gonna have to change them all to AC. All right, so I'm all instrumentated up. I got myself as AC components. I'm going to go change this to Tera so that it doesn't interfere with my anything except how long it's going to take to do the calculations. But I don't want any spare ohms showing up someplace that's going to hose me over later. And so everything is an AC. So now the issue is, how do I get 180 if that's equal to 2 pi 60 hertz times L? So L is going to be 180 divided by 2 pi 60. So we take out our calculator. 180 divided by 2. Do I get a pi? I don't get a pi. Divided by 3.1415 divided by 60 equals. So I need a 0.477 Henry inductor. Okay, 0.477 Henry. All right, and then I got to do the same thing. 180 is equal to 1 over 2 pi FC. So C is going to be 1 over 2 pi 60 180. All right, so I get my calculator out. 2 times 3.1415 times 60 times 180 equals, do I have a 1 over key? 1 over. Is there a plus minus key? I don't see a plus minus key.
There's a 1 over right above equals.
Where?
Right above the equal sign.
Oh yeah. All right, so I got to do it again because I hosed it over. 2 times pi times 60 times 180 equals 1 over. So it looks like I need 14.7 microfarads. Fourteen point 7 micro. All right, so all things being equal, I should see K, 101,000. Am I off by 1,000? What? What did I do wrong?
I think you put it under 20.
Oh, the source, okay. So I'm off by 100 because I am off by 100. Is that what you're trying to tell me? 12 volts. I'm off by a factor of 10 because I'm off by a factor of 10, not because I did anything wrong. So that looks pretty close. You know, we'd have to throw in some more significant digits if we wanted to get any closer to that. So there's my 12 volts across the resistor, my 0 volts across the whole thing. Close enough, right? And then there we go, there and there. I didn't keep any more significant digits than that, but I could have thrown 3 or 4 more significant digits in if I wanted to, and gotten closer to reality. Okay, so that's the issue. The issue is that that these guys are sending currents back and forth to each other that are 180 degrees out of phase. Total current's going to be the same. It didn't change any, but I have huge amounts of voltage across the inductor and the capacitor. That is something that I can feel. Even though it's imaginary numbers in the math, I can put my fingers across that and I can feel 120 volts. Now, you're not going to be able to feel 5 volts because that's not very much. You've got to get up to about 22 or so. I forget who did that. I think it was Joel that did that last. Cranked up the voltage on his tongue until he could feel it.
You feel 12 on your tongue.
12 on your, well, it all depends how much you drank that day. 19, 20, I just made that up. 25, no, 23. 23. Determine the magnitude and phase angle of the source voltage.
23.
Yeah, 23, yeah. So I got some source voltage. And this is the same problem you're doing in your labs, right? Yeah, you're doing the same type of thing, except your pictures are prettier than mine. So I got 12 volts, 12 volts, 5 volts. All right, so the, oh, I got the picture turned around, don't I? I knew the picture was bad, but I didn't realize it was that bad. That even Raimundo could figure out it was bad. I mean, that is really bad. Right? Right, so the voltage of the source is equal to the square root of the voltage across the capacitor squared plus the difference between these two guys, which is 7. So 12 minus 7 squared. No, 12 minus 5. 12 minus 5 squared. So the voltage across the source, 144 plus 49 equals square root. Is that a square root? 13.9 volts. 13.9 volts. The phase angle is going to be the arctangent of the y component, which is 7 over 12, and it's positive because the guy wins. Okay. Back to my calculator. 7 divided by 12 equals inverse tangent. 30.2 degrees. Okay. So much for 23. Is that all I needed to do? That's all I needed to do. We could write a final answer. Final answer. Voltage source is 13.9 volts, angle 30.2 degrees. So we could do that, and then we could put a box around it maybe. That'd be overachieving though. If I did something like that, that'd be overachieving. 31. Hope we get something good like a parallel. Oh, there we go, a parallel one. Calculate the impedance, the current, and the voltages for A. Okay, so I got that, I got this, 330 ohms. Way to go, 22 millihenry. Why don't you just do the calculation for me so I don't have to do it? 0.1 microfarad. And I'm at 2 volts, 12 kilohertz. All right, so I need to find x sub L. 2 pi 12K 22 millihenry. All right. What happened to my calculator? Somebody must have turned it off. Who came up here and turned off my calculator when I wasn't looking? 2 times 3.141592 times 12 times 22. The kilo and the milli cancel each other out, so I don't have to put them in. 1.66K. 1.66K ohms. And I probably don't have 3 significant digits, but I'm going to carry 3 just for the heck of it for now. X sub C, 1 over 2 pi 12K, and we'll call it 100 nano. Okay, so now that I found my 1 over key, I'm all set. 2 times 3.141592 56 times 12 1 2 3 of those guys times 100 double E minus, oh, bummer. Just as I was doing good too.
The micro nano.
1 is not, it's nano now. Clear everything. 100 exponent 9. Now how do I get it to be minus? That guy? Oh, yes. Oh, that was so good. 12 1 2 3 times 2 times 3.141592 equals 1 over key 132 ohms, if I did it right. Okay, so X of S, the part that only has the inductive stuff in it, that's going to be 1.66K minus 132, which is going to be 1.53 K ohms, angle 90 degrees because the inductor wins. All right. Now,
Is that positive 90?
yeah, it's a positive 90. Want me to rewrite it so it looks better? So I can move it over some, have more room. Angle 90 degrees. Is that better?
Much.
All right, so I'm looking for the impedance. Impedance is going to be 1 over, that's the resistor. 330. 330 angle 0 plus 1 over 1.53 angle 90. Now this is where, if I had a better calculator, I'd be all set, right? All right, so back to my calculator. 3301 over key. 0.330. 0.0, was it 0.003? 0303 plus, I did it again. I got rid of my calculator again. I don't believe it. 3301 over. Yeah, that's right. Okay. The other guy was what? 1 Forgot already.
1,530.
153. 15301 over. Why do I have to put up with that? 0.00065. 0.00065 angle minus 90. Alright, so now I'm going to go and do a square root of 0.0030303 squared plus 0.00065 squared, and I'm going to find the magnitude of what I had down below, and then I'm going to take the angle is going to be the arc tangent of minus 0.00065 divided by 0.003. Or is it the other way around? It's the other way around. Nope. I was right. All right, 0.00065. Okay, that's what I'm going to do. Okay, so back to my calculator. I have the first guy already in my calculator. I'm going to square him. If I could find my square key. Squared plus 0.0030303 squared equals square root. Looks like a 0.0031. 0.0031. And my angle is going to be 0.00065 divided by 0.003 equals inverse tangent 12 degrees. 12.2 degrees. Alright, so now I've got my impedance is 1 over 0.0031 angle 12.2 degrees. And I'm almost where I want to be. Back to my calculator. 0.0031 1 over 322. 322 ohms and an angle of minus 12.2 degrees. So that's going to be my impedance. Was I asked to calculate impedance? Yes. Calculate the impedance, the current, and the voltage. Okay, so I have the impedance. Fine. All right, now I'm going to find total current. What's total current? 2 volts divided by 322 ohms. Angle minus 12.2. Okay, so my angle is going to be 12.2. All right. 2. Okay, I have that number already. 1 over times 2 equals 0.00006. We'll call it 6.2 milliamps. 6.2 milliamps. Okay. Now I got to find the current in each component and the voltage. Okay, I'm going to go way out on the limb and say the voltage across the resistor is going to be 2 volts. Anybody disagree with that? Yeah, it looks like it, right? 2 volts. All right. So we got that one. Now I'm going to find, now that I know that, I can now find the current through the resistor. 2 volts divided by 330 ohms. Okay, so 2 volts divided by 330 ohms. 2 divided by 330. 0.006. 06. All right, so we'll call it 6.06 milliamps. All right, now we have 6.2 milliamps total current at an angle of 12 degrees, and we have 6.06 milliamps going through the resistor. So this is pretty close to whatever, right? So I'm just going to subtract those two guys and say the current through the inductive part of the system is 6.2 milliamps minus 6.06 milliamps. And I'm going to say that that's close enough and call it 40 microamps. Now, the other alternative would be to take 6.2 milliamps angle 12.2 and subtract it from 6.06 milliamps. That would be the other alternative. So let's see how close we get if we do that. So if I go to my calculator and I go 6.2 times 12.2 cosine equals 6.06. 6.06 plus, and then I look for the sine component, 6.2 times 12.2 sine equals 1.3 J minus 6.06 milliamps. So I would have the current through the inductive branch be 1.3 milliamps. What did I call it before? Oh, maybe that would be a better answer than that is. Okay, so we'll cross this out saying I don't want to do that. I really do want to find what it is. Yeah.
Should have been 140, not 14.
What should be 140?
The current through the...
Oh, this guy here should have been 140?
Yeah.
Which is pretty darn close to what I had.
Yeah.
Well, luckily I have an undo button. Okay, so if this would have said 140 microamps, that's pretty close to, that's still pretty far away from 1.3 milli. So I'm still going to have to do it this way, and I'm still going to have to call this other guy wrong. Nice approximation, but wrong. All right, so that being the case, my voltage across the inductor, 1.2 milliamps times something. Voltage across the capacitor, 1.3 milliamps times something. What are those somethings? 1.66K and 132. 1.66K and 132 ohms. There are angles associated with both of those things, right? So this guy here has an angle of 90 degrees. So this guy's got an angle of 90 degrees. This guy's got an angle of 90 degrees. This guy's got an angle of 90 degrees. This guy has an angle of minus 90 degrees. Okay, back to what we're doing. 1.3 exponent 3 plus minus times 1660, 2.1 volt angle 180. All right, out of room again. 2.1 volt angle 180 degrees. This other guy, 0.0013 times 132. Boom. 170 millivolts, angle 0 degrees. So I've calculated the current, I've calculated the voltage, and I've calculated the impedance, and I've calculated everything there's to do, and that only leaves problem number 37, which we can't do because it's not on this page. Will somebody come over and turn my page for me in my book? So never mind, I'll do it myself. It's checking out this, what's going on. See, if we get rid of this, then we don't have to look at it. 37. Calculate the impedance, the current, the voltage of the A guy. Oh, good thing it's the A guy, not the B guy. All right, so I got something here. 10 volts, 1K. Got a capacitor, 0.22 microfarad. Got an inductor, 47 millihenry. I think we had one of them before, didn't we? Resistor, 510 ohms. Capacitor, 0.22 microfarads. All right. Got it. Okay, so I'm going to find x of c. 1 over 2 pi 1000 times 0.22 microfarads. 2 times 3.141592 times 1000 times 0.22 exponent 6 plus minus key equals 1 over 723 ohms angle minus 90 degrees. And we're going to find x of L. 2 pi 1047 millihenry. Hope I don't fall asleep during this problem. 2 times 3.141592 times 47 equals 295 ohms angle 90 degrees. Okay, so I'm going to look for the impedance in the series path, and that's going to be 510
Impedance?
squared plus what? 723 squared equals. Okay, so 510 squared plus 723 squared equals square root 884 ohms, and my angle is going to be the arctangent of, and it's going to be negative 723 divided by 510. 723 divided by 510 plus or minus key equals inverse function tangent minus 54 degrees. Minus 54 degrees. Okay, now I'm going to find the impedance in the parallel path. 1 over what? 295 angle 90 plus 1 over 884 angle minus 54. Okay, so that's what I'm going to do. In the parallel path, 1 over 295, 1 over 0.00339. 0.00339 angle minus 90 plus no point at all, 884 1 over 0.00113 0.00113 angle positive 54. Okay, then we're going to go and say this is 0 plus 0.00339, that's a minus sign, minus j, and now we're going to get the sine and cosine of this guy, plus 0.00113 times 54 cosine equals 0.000664 plus, and then we're going to go 0.00113 times 54 sine point something's wrong. I don't know what it is. My trifocals can't tell me, but there's something wrong. 0.00113 times 54 sine. I must have hit the hyperbolic sign. That's still hosed. Yeah, but it's got to be something smaller than 0.0011. 54, clear entry, 54 sine. Oh, I didn't hit the equal key, you dummy, times 0.00113 equals, yeah, that's better, 0.000914 J. Okay. 1 divided by 0.000664 minus. Okay, so I've got the number I have there minus 0.00339 equals 0.00248 J. Alright, now I'm going to find the magnitude, 0.000664 squared plus 0.00248 squared equals square root 0.00257. 0.00257, and then we're going to find the angle. Okay, before we do that, we're going to hit the 1 over key. 398.5.
89.
We'll call it 390. Okay, so we're going to call this 390 ohms angle. So now we're working on the angle. So I need the arc, tangent of minus 0.00248 divided by 0.000664. That's what I'm looking for. 0.00248 plus minus key divided by 0.0000664 equals inverse function tangent minus 75 degrees, making this 75 degrees. Okay, so that's the impedance of the parallel path. So now the impedance total, impedance is going to be the resistor guy. No, it's not a resistor. It's that capacitor. What's the capacitor? 723 angle minus 90 plus 390 angle 75. Okay, so this is minus 723J plus some number. 390 times 75 cosine equals, call it 101. 101 plus 390 times 75 sine equals 376J. So my impedance is going to be 101 minus 723 ohm is going to be minus 346 J. Okay, so now we're on a magnitude. We're going to take this guy square M
What's the answer?
plus 101 square M equals square root 360. So it's going to be 360 ohms angle. Now we want the angle, so we're going to go and take 346 plus minus key divided by 101 equals inverse tangent minus 73 degrees. All right, so now I've found the impedance, so I've calculated it. Excellent. Now I'm going to find the total current. So current total is going to be voltage, 10 volts. 10 volts divided by 360 ohms, angle minus 73 degrees. And I'm going to have an angle of positive 73 degrees. 10 divided by 360, we'll call it 28 millivolts. Oh, millivolts. Current is in amps, milliamps. Okay, now we're going to find the voltage across capacitor 1. Voltage across capacitor 1. 28 milliamps, angle 73 degrees, times 723 angle minus 9. 723 ohms, angle minus 90. Alright, so I'm going to go 28 times 0.723 ohm. 20 volts. 20.2 volts. 20.2 volts, angle minus 19. 19. Alright, so I got the voltage across the capacitor. Okay, now I'm going to look at the voltage across.
17, isn't it?
It is?
90 minus 17 would be 17.
Okay, I think so. All right, we'll go with 17. The voltage across the parallel path is going to be 10 volts minus the 20.2 volts angle minus 17. All right, so that's 10 volts minus. Okay, so I need, how come my calculator is way down there? How come it's not up here where I need it? 20.2 times 17 with a minus sign cosine equals 19.3, and then I need 20.2 times 17 with a minus sign equals minus, I couldn't read it, 5.9 J. So the voltage across the parallel path minus 9.3 volts. We wouldn't really put the volts there. 9.3 plus 5.9 J. Okay, we want that in polar form. 9.3 squared plus 5.9 squared equals square root 11. 11 volts angle. Okay, angle. Oh, I don't know about this. 9.3 with a minus sign. We don't want that. We want the other way around. Clear, clear. 5.9 divided by 9.3 with a minus sign equals arc tangent. Minus 23 degrees. Minus 32 degrees. Now, this answer is a second quadrant answer. So the real answer is not that. The real answer is this, 180 minus 32. So 180 minus 32 would be 148 degrees. That's right?
Yeah.
Okay. Well, what did I just calculate? Okay, so that's the voltage on the parallel path. All right, so now that I know the voltage of the parallel path,
There's more.
shit, I'm only halfway done.
Much more.
I haven't just got warmed up. So we want the voltage across the inductor. 11 volts, angle 148. We just calculated, right? The voltage, the current through the inductor. 11 volts, 148, divided by, what is the reactance of the inductor? That was way up here. There it is. 290 angle 90. 290 angle 90. Is that right? 295 angle 90. All right. So I'll get the angle first. Angle is 58 degrees. Okay. Take my calculator. 11 divided by 295. 37.2. 37.2 milliamps. Okay, now the current through the series path of the resistor and the capacitor is total current minus the current that goes through the inductor. Okay, so anybody remember what the total current was? There it is, 28 milliamps. 28 milliamps angle 73 degrees minus 37.2 milliamps angle 58 degrees. Okay. So now I'm going to have to break these into their XY components. 28 times 73 cosine equals 8.2. 8.2 plus 28 times 73 sine equals 20, we'll call it 27. 27J minus 37.2 times 58 cosine equals 19.7 plus 37.5, that isn't right, 37.2 times 58 sine equals 31.5J. Alright, so I got 19.7 minus 8.2, 11.5. 11.5 minus, is that 4.5? 4.5J. Okay. It's going to give me a magnitude of, we're going to square this guy, plus 4.5 squared equals square root 12.3. 12.3. What is it? I'm calculating current, right? And everything's in milliamps. So it's going to be milliamps angle. Okay, so angle 4.5 on the top with a negative sign divided by 11.5 equals, where's my negative sign? Boom. Inverse tangent minus 21 what? 21.4 degrees. So that's my current through that. Okay, so my voltage across the resistor and voltage across capacitor 2 is 12.3 milliamps, angle minus 21.4, and 12.3 milliamps, angle minus 21.4, times the resistor, 550, 510, and that capacitor, 723 angle minus 90, right? Okay, minus 90. Alright, so we have to calculate those two numbers. I've got this guy already. No, that's the number of degrees I got. 12.3 times 510. 6,200 volts, 270 volts. That's quite a bit. Oh, this is milli. Put the point there.
6.2.
We'll call it 6.3. 6.3 volts. All right. Now the guy down below, 12.3 times 0.723, 8.9 volts. This is angle minus 21.4, I think. And this is angle minus 111.4. Now, at that point, we've calculated everything that can be calculated. So now the only issue is the answer in the back of the book? And if it is, are we right? Are you laughing because it is and I'm wrong? Or are you laughing because it's not there and I'll have to do it in Molisem to see if my answer's right, and you guys will have to stay here for another half hour while I do it?
Did 3 pages to get
Huh?
this?
14. That was only one page. 14.
3 pages.
That was 2 pages. 2 for me.
Oh, bummer. It's not there.
Oh, I'm a math genius,
It only goes
so
to.
I think this is right.
You think this is correct?
I think it's correct.
Right. Well,
I
no.
just got a good vibe about
Every single time I made a mistake, you guys corrected me, right?
it. Yeah.
Yes, we did.
Yeah, so it must be correct. So, why not?
Hopefully it works out well.